Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the annals of scientific history, 1905 stands as an exceptional year, a true annus mirabilis, largely because it witnessed Albert Einstein's extraordinary outpouring of groundbreaking papers. Among these remarkable contributions, his work on the movement of small particles suspended in liquids at rest required by the molecular kinetic theory of heat offered a profound explanation for Brownian motion, forever changing our understanding of matter and providing compelling evidence for the existence of atoms and molecules, a concept still debated by some prominent scientists at the time. This paper, often overshadowed by his work on special relativity, holds significant importance in the development of statistical mechanics and the validation of atomism. The genesis of Einstein's paper lies in the persistent puzzle of Brownian motion, first observed in 1827 by the botanist Robert Brown while examining pollen grains suspended in water. This erratic, perpetual movement of microscopic particles defied explanation. By classical physics, scientists initially suspected the motion arose from external factors, such as convection currents or vibrations. However, careful experimentation revealed the motion to be intrinsic, independent of external disturbances, and dependent on both the size of the particles and the temperature of the liquid. A diverse group of scientists and mathematicians contributed to the theories surrounding Brownian motion during the 19th century, including physicists Christian Wiener, Louis Georges Gauy, and Henri Poincaré. Their contributions provided greater evidence for the phenomenon and its underlying mechanisms as they could provide no quantitative predictions or tie the cause of the particle movements to the kinetic theory of Einstein's approach was revolutionary. Departing from purely observational descriptions, he applied the principles of statistical mechanics to model the movement of the suspended particles. He reasoned that if liquids are composed of discrete molecules in constant thermal motion, as the kinetic theory of heat posited, then these molecules would bombard the suspended particles randomly from all directions. Although the average force exerted by these collisions would be zero, instantaneous imbalances would result in the erratic motion observed by Brown. To formalize this idea, Einstein made several crucial assumptions. He assumed that the suspended particles were much larger than the liquid molecules, allowing him to treat the liquid as a continuous medium influencing the particle's motion through a frictional force. He assumed that the motion of a particle in one direction was independent of its motion in any other direction. He further assumed that the collisions between the liquid molecules and the suspended particle occurred randomly, adhering to the laws of probability. Based on these assumptions, Einstein derived a formula for the mean squared displacement of a particle in a given time interval. Specifically, he showed that the mean squared displacement, denoted by delta squared, is related to the diffusion coefficient d, and the time interval t by the equation delta squared equals 2 times d times t. Here, delta represents the displacement of the particle along a specific axis. Einstein then related the diffusion coefficient d to measurable quantities such as the temperature T, the viscosity of the liquid ether, and the radius of the particle through the equation d equals kt divided by 6 pi eta a, where k is the Boltzmann constant. By measuring the mean squared displacement of particles of known size in a liquid of known viscosity at a given temperature, one could determine the value of Boltzmann's constant and, consequently, Avogadro's number, a fundamental constant in chemistry and physics. Einstein's theoretical predictions delivered testable relationships between observable quantities and molecular properties. This enabled experimental verification of the molecular kinetic theory. Prior to this, the existence of atoms and molecules was still viewed with skepticism by some prominent scientists, including Wilhelm Ostwald, who favored energeticism, a theory emphasizing energy as the fundamental constituent of the universe over matter. Einstein's work, by providing a quantitative link between microscopic molecular motion and macroscopic observable phenomena, provided the strongest evidence to date for the physical reality of atoms and molecules. The brilliance of Einstein's approach laid in its ability to utilize readily measurable parameters to predict molecular behavior. The immediate impact of Einstein's work manifested in the experimental efforts led by Jean-Baptiste Perrin between 1908 and 1911. Perrin meticulously conducted experiments to measure the Brownian motion of microscopic particles of uniform size. Using microscopic observations, he painstakingly tracked the positions of these particles over time, calculating their mean squared displacements. Perrin's results agreed remarkably well with Einstein's theoretical predictions, providing strong empirical support for the molecular kinetic theory and convincing many remaining skeptics, including Ostwald, of the reality of atoms. Perrin was awarded the Nobel Prize in Physics in 1926 for his work on the discontinuous structure of matter, largely attributed to his verification of Einstein's theory of Brownian motion. It is testament to the profound impact of Einstein's theoretical work that it directly led to experimental confirmation and subsequent recognition. With science's hires, the influence of Einstein's work on Brownian motion extends far beyond providing evidence for atomism. His approach paved the way for the development of stochastic processes, mathematical models describing systems evolving randomly over time. These processes find applications in diverse fields, including finance, where they are used to model stock prices, and biology, where they are used to describe the movement of molecules within cells. Norbert Wiener, building upon Einstein's work, developed a rigorous mathematical theory of Brownian motion, known as the Wiener process, which forms the basis of stochastic calculus, a powerful tool used in mathematical finance and other areas. Kiyoshi Ito further generalized Wiener's work, developing Ito calculus, which allows for the analysis of stochastic differential equations that describe the evolution of systems influenced by random. Furthermore, Einstein's treatment of Brownian motion provided a blueprint for understanding other transport phenomena, such as diffusion and thermal conduction. The concept of relating macroscopic transport properties to microscopic molecular motion, pioneered by Einstein, became a cornerstone of statistical mechanics, influencing later developments by researchers such as Lars Onsager, who developed the theory of irreversible thermodynamics, and Harry Nyquist, who studied thermal noise in electrical circuits. The approach proved exceptionally potent when applied to systems whose underlying dynamic behavior was on. Despite its profound success, Einstein's theory of Brownian motion faced some initial critiques. One concern centered on the assumption of independent collisions between liquid molecules and the suspended particle. Critics argued that the liquid molecules themselves interact, potentially leading to correlated collisions that would invalidate Einstein's calculations. However, subsequent theoretical work, incorporating the effects of hydrodynamic interactions between the liquid molecules, demonstrated that these correlations had a negligible effect on the mean-squared displacement of the particle, validating Einstein's initial simplifying assumption. Additionally, the mathematics behind Brownian motion proved initially difficult for some to grasp. Its reliance on statistical concepts and probabilistic modeling represented a shift from deterministic descriptions, favored by many physicists at the time. This initial resistance, however, gradually waned as experimental evidence mounted and the power of Einstein's approach became increasingly. Einstein's work built upon previous insights from scientists such as Ludwig Boltzmann, whose work on statistical mechanics provided the theoretical foundation for understanding the relationship between microscopic molecular motion and macroscopic thermodynamic properties. Boltzmann's work demonstrated how the kinetic theory of gases could explain macroscopic phenomena such as pressure and temperature in terms of the average kinetic energy of the gas molecules. Einstein extended Boltzmann's ideas to liquids, providing a quantitative theory for Brownian motion that could be experimentally verified. The influence of Einstein's Brownian motion paper on subsequent scientific work is immense and undeniable. In a paper published 1 year later, Murray and Smolarchowski independently derived similar conclusions regarding Brownian motion to those of Einstein. Smolarchowski's work emphasized the role of statistical fluctuations in physical phenomena and contributed to the development of the theory of coagulation. His work, though independent of Einstein's, provided further support for the molecular kinetic theory and solidified its place in the scientific canon. Paul Langevin, in 1908, provided a different approach to modeling Brownian motion, using a stochastic differential equation now known as the Langevin equation. Langevin's approach, while mathematically distinct from Einstein's, yielded equivalent results and provided a more intuitive understanding of the forces acting on the Brownian particle. In conclusion, Albert Einstein's 1905 paper on the movement of small particles suspended in liquids at rest required the molecular kinetic theory of heat represents a watershed moment in the history of physics. By providing a theoretical explanation for Brownian motion and connecting it to the molecular kinetic theory, Einstein furnished compelling evidence for the existence of atoms and molecules. The effect shifted the paradigm away from abstract thought and towards concrete proofs. His work not only revolutionized our understanding of matter, but also laid the groundwork for the development of stochastic processes and other important concepts in statistical mechanics. It is a testament to the enduring power of theoretical physics that Einstein's insights, born from thought experiments and mathematical reasoning, continue to shape our understanding of the world at its most fundamental level. The paper demonstrated the power of bridging theory and experiment, forever altering the course of scientific discovery. It serves as a timeless example of how intellectual curiosity, combined with rigorous mathematical analysis, can unlock the secrets of the universe one jiggling particle at a time.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.